Chapter 9, Light, Reflection and Refraction. This chapter covers two key phenomena of light. First, reflection, light bouncing off a surface. We study spherical mirrors, concave and convex. Second, refraction, light bending as it passes from one medium to another because its speed changes. For mirrors, we use the mirror formula, 1 over V, plus 1 over U, equals 1 over F, magnification M equals negative V over U. For lenses, we use the lens formula, 1 over V, minus 1 over U, equals 1 over F. We also study the power of a lens, measured in dioptres. Reflection is when light falls on a surface and bounces back into the same medium. There are two types. Regular reflection, also called specular reflection, occurs on smooth polished surfaces like mirrors. Parallel rays reflect as parallel rays. Diffuse reflection occurs on rough surfaces, like walls, where rays scatter in all directions. Now, the two laws of reflection. First law, the angle of incidence equals the angle of reflection. Both angles are measured from the normal to the surface at the point of incidence. Second law, the incident ray, the normal at the point of incidence, and the reflected ray, all lie in the same plane. A spherical mirror is a mirror whose reflecting surface is part of a hollow sphere. A concave mirror has its reflecting surface curved inward, like the inside of a spoon. It is a converging mirror. It brings parallel rays to a focus in front of the mirror. A convex mirror has its reflecting surface curved outward, like the back of a spoon. It is a diverging mirror. Parallel rays spread apart after reflection and appear to come from a focus behind the mirror. An important relationship, the focal length f equals half the radius of curvature r. So f equals r divided by 2. The pole P is the midpoint of the reflecting surface of the mirror. The center of curvature C is the center of the full sphere the mirror is part of. The distance from the pole to C is the radius of curvature r. The principal axis is the straight line passing through the pole P and the center of curvature C. The principal focus F is the point on the principal axis, where rays parallel to the axis converge for a concave mirror. In case of convex mirror, it is the point from which the rays appear to diverge from, after reflection. The focal length f is the distance from the pole P to the principal focus F. Remember, f equals r over 2. For a concave mirror, f is in front of the mirror. It is a real focus. For a convex mirror, f is behind the mirror. It is a virtual focus. To draw ray diagrams for concave mirrors, we use two standard rays. Ray 1, a ray parallel to the principal axis. After reflection, it passes through F. Ray 2, a ray passing through F. After reflection, it goes parallel to the principal axis. Case 1, object at infinity, parallel rays converge at F, image forms at F, it is real, inverted, and point-sized, highly diminished. Case 2, object placed beyond the center of curvature C. Ray 1 is drawn parallel to the principal axis. After reflection, it passes through the focus F. Ray 2 passes through F, and after reflection, it travels parallel to the axis. Both rays meet between F and C, where the image is formed. The image is real, inverted, and diminished. Now case 3, object placed at the center of curvature C. Ray 1 is again drawn parallel to the axis, and reflects and passes through F. Ray 2 passes through F and reflects back parallel to the axis. Both rays meet at C on the other side. The image is real, inverted, and the same size as the object. Pattern: as the object moves from infinity toward F, the image moves from F outward, always real and inverted when the object is beyond F. Case 4. Object is between C and F. Ray 1 travels parallel to the axis and reflects through F. Ray 2 passes through F and reflects parallel. The two rays converge well beyond C. The image forms beyond C, real, inverted, and magnified. Case 5. Object is placed at F itself. Ray 1 travels parallel to the axis and reflects through F, but since the object is at F, the reflected ray heads far down and to the left. Ray 2 travels from the object to the pole and reflects at the same angle. Both reflected rays are parallel, they never meet. The image forms at infinity. As the object moves from C toward F, the image moves farther beyond C, growing larger and larger until it reaches infinity when the object is at F. Case 6. Object is between F and P, very close to the mirror. Ray 1 travels parallel to the axis and reflects through F. Because the object is closer than F, the reflected ray diverges, it heads downward to the left. Ray 2 travels from the object to the pole and reflects. This ray also diverges. Extending both rays backward behind the mirror, they meet at a point behind the mirror. The image is virtual, erect, and magnified. Summary of concave mirror image formation. This table explains how the image is formed, for various positions of the object, along the line of the principal axis. Only when the object is between F and P does the concave mirror produce a virtual image. In all other positions, when the object is beyond F, the image is real and inverted. This is why concave mirrors are used as shaving and makeup mirrors. They give a magnified, upright reflection when held close. A convex mirror always produces a virtual, erect, and diminished image, regardless of where the object is placed. Case 1. Object at infinity. All incident rays are parallel to the axis. Ray 1 hits the mirror and reflects as if it came from F behind the mirror, it diverges upward to the left. Ray 2 also travels parallel, lower on the mirror. Its reflected ray diverges downward to the left. Both backward extensions meet at F, giving a virtual, point-sized image at F. Case 2. Object anywhere between infinity and the pole. The object is in front of the mirror. Ray 1 travels parallel to the axis. After reflection it diverges, appearing to come from F behind the mirror. Ray 2 travels from the object top to the pole and reflects at an equal angle on the other side of the axis. Extending both reflected rays backward, they meet between P and F, giving a virtual, erect, diminished image. Because the image is always virtual, erect, and diminished, a convex mirror gives a wider field of view. This is why it is used as a rear-view mirror in vehicles and as a security mirror in shops. We use the new Cartesian sign convention. The origin is the pole P of the mirror. Distances measured in the direction of incident light, from left to right, are positive. Distances measured against the direction of incident light are negative. Heights above the principal axis are positive. Heights below are negative. For mirrors, the object is always placed to the left of the mirror. So the object distance U is always negative. Concave mirror, the focus F is in front, to the left, so F is negative. Convex mirror, the focus F is behind, to the right, so F is positive, and R is also positive. Real images form in front of a mirror, V is negative. Virtual images form behind the mirror, V is positive. The mirror formula relates the object distance U, image distance V, and focal length F. The formula is 1 over V, plus 1 over U, equals 1 over F. All distances must be in the same unit and the sign convention must be applied. Worked example: an object is placed 15 cm in front of a concave mirror with focal length 10 cm. Find the image distance. Here, U equals -15, F equals -10, and we need to find V. Substituting the values, we get 1 over V equals -1 over 30. So V equals -30 cm. The negative sign confirms the image is real and forms 30 cm in front of the mirror. The mirror formula works for both concave and convex mirrors, just apply the sign convention correctly. Magnification is the ratio of the height of the image to the height of the object. The formula is m equals height of image over height of object, which equals -V over U. If m is negative, the image is inverted. This corresponds to a real image. If m is positive, the image is erect. This corresponds to a virtual image. If the magnitude of m is greater than 1, the image is magnified. The image size is larger than object. If the magnitude is less than 1, the image is diminished. The image size is smaller than object. If the magnitude equals 1, the image is the same size. For a convex mirror, m is always positive and less than 1, virtual, erect, diminished. For a concave mirror, object between P and F, m is positive and greater than 1, virtual, erect, magnified. Concave mirrors have several important uses. Doctors, dentists and ENT specialists use them to examine teeth, ears, nose, and throat. The patient is placed between P and F, giving a magnified, erect, virtual image. Concave mirrors are also used as shaving and makeup mirrors for the same reason. In torches, searchlights, and vehicle headlights, the light source is placed at F, producing a strong parallel beam of light. In solar furnaces, a large concave mirror focuses sunlight at a single point to generate very high temperatures. Convex mirrors are used as rear-view mirrors in vehicles. The always virtual, erect, diminished image gives the driver a wider view of traffic behind. They are also used as security mirrors in shops and at blind road curves. Note: plane mirrors are used in periscopes, kaleidoscopes, and in barber shops. 2 plane mirrors let you see the back of your head. Refraction is the bending of light when it travels from one transparent medium to another. It happens because light changes its speed at the interface. When light enters a denser medium, for example, from air into glass, it slows down and bends towards the normal. The angle of refraction is less than the angle of incidence. When light enters a rarer medium, for example, from glass into air, it speeds up and bends away from the normal. The angle of refraction is greater than the angle of incidence. If light hits the surface exactly along the normal, at 90 degrees to the surface, it passes straight through without bending. Everyday examples of refraction: a pencil in a glass of water appears bent at the surface. A swimming pool appears shallower than it actually is. Stars appear to twinkle because light refracts through layers of the atmosphere. There are 2 laws of refraction. First law: the incident ray, the refracted ray, and the normal to the interface at the point of incidence, all lie in the same plane. Second law, also called Snell's law: the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. In formula, sin I divided by sin r equals a constant n. More generally, Snell's law is written as n1 sin theta 1 equals n2 sin theta 2, where n1 and n2 are the refractive indices of the 2 media. The refractive index n of a medium tells us how much light slows down in that medium, compared to vacuum. The absolute refractive index is n equals c divided by v, where c is the speed of light in vacuum, and v is the speed of light in the medium. The relative refractive index of medium 2 with respect to medium 1 is n12 equals v1 over v2, which equals n2 over n1, which also equals sin I over sin r. Common values to remember: air is approximately 1.0, water is approximately 1.33, glass is approximately 1.5, diamond is approximately 2.42. Higher refractive index means the medium is optically denser, light travels slower, and bends more towards the normal when entering from air. When a ray of light passes through a rectangular glass slab, which has two parallel surfaces, it undergoes refraction at each surface. At the first surface, air to glass, the ray slows down and bends towards the normal. At the second surface, glass to air, the ray speeds up, and bends away from the normal by exactly the same amount. The result, the emergent ray is parallel to the incident ray. But it is shifted sideways. This shift is called lateral displacement. Lateral displacement increases with the thickness of the slab, with a larger angle of incidence, and with a higher refractive index. At normal incidence, that is, 0 degrees, there is no lateral displacement. A lens is a transparent medium, usually glass, bounded by two curved surfaces, at least one of which is spherical. Lenses form images by refraction. A convex, or biconvex, lens is thicker at the center and thinner at the edges. It is a converging lens. It focuses parallel rays to a real point on the other side. A concave, or biconcave, lens is thinner at the center and thicker at the edges. It is a diverging lens. Parallel rays spread apart after passing through, and appear to come from a virtual focus on the same side as the incoming light. Lenses work by refraction. Light bends at each surface as it passes through the lens. Memory aid, convex, converging, like a magnifying glass. Concave, diverging, like the corrective lens for short-sightedness. The optical center O is the central point of the lens. A ray passing through O passes straight through without any deviation. The principal axis is the straight line passing through the centers of curvature of both surfaces and the optical center. The principal focus F is where parallel rays converge, for a convex lens, or appear to diverge from, for a concave lens, after refraction. A lens has two foci, f1 on the side of the incoming light, and f2 on the other side. The focal length f is the distance from the optical center to the principal focus. For a convex lens, f is positive. For a concave lens, f is negative. For ray diagrams, use three standard rays. One parallel to the axis passes through f2 after refraction, one through the optical center passes undeviated, and one through f1 emerges parallel to the axis. For lenses, we use the same new Cartesian sign convention, but the origin is now the optical center O. Distances in the direction of incident light, to the right, are positive. Distances against the incident light, to the left, are negative. Object is always to the left of the lens, so the object distance u is always negative. Real images form on the right side, opposite to the object, so v is positive for real images. Virtual images form on the left, same side as the object, so v is negative for virtual images. Convex lens, f2 is on the right, f is positive, power is positive. Concave lens, f2 appears to be on the left, f is negative, power is negative. Key difference from mirrors: for lenses, real images have positive v. For mirrors, real images have negative v. This is because real images and the object are on opposite sides of a lens, but on the same side of a mirror. Heights above the principal axis are positive, below are negative, same as mirror convention. To draw ray diagrams for a convex lens, we use three standard rays. Ray 1, a ray parallel to the principal axis. After refraction, it passes through f2, the second focus, on the right side of the lens. Ray 2, a ray directed toward the optical center O, passes straight through without any bending. Ray 3, a ray directed toward f1, after refraction, it goes parallel to the principal axis. Case 1, object at infinity, all incident rays are parallel to the axis. After refraction they converge at f2, image is real, inverted, and highly diminished, point-sized. Case 2, object placed beyond 2f1, farther from the lens than twice the focal length. Ray 1 is drawn parallel to the principal axis. After refraction it passes through f2. Ray 2 passes through optical center O in a straight line. Ray 3 is directed toward f1, after refraction it emerges parallel to the principal axis. All three rays converge between f2 and 2f2. The image is real, inverted, and diminished. Now case 3, object placed exactly at 2f1. Ray 1 again travels parallel and refracts through f2. Ray 2 goes through O without deviation. Ray 3, directed toward f1, emerges parallel after refraction. All three rays meet exactly at 2f2. The image is real, inverted, and the same size as the object. Pattern: as the object moves from infinity toward 2f1, the image moves from f2 toward 2f2, always real and inverted. Case 4, object between f1 and 2f1. Ray 1 travels parallel to the axis and refracts through f2. Ray 2 goes through O in a straight line. Ray 3 is directed toward f1 and emerges parallel to the axis after refraction. All three rays converge well beyond 2f2. The image is real, inverted, and magnified, larger than the object. Case 5, object placed exactly at f1. Ray 1 travels parallel and refracts in the direction of f2. Ray 2 goes through O with the same slope as Ray 1. Both refracted rays are parallel and never converge. The image forms at infinity. As the object moves from 2f1 toward f1, the image moves farther beyond 2f2 until it reaches infinity when the object is at f1. Case 6. Object placed between O and f1, closer to the lens than the focal length. Ray 1 travels parallel to the axis and refracts toward f2 on the right side. Tracing this refracted ray backward, to the left of the lens, gives us the apparent direction it came from. Ray 2 passes through O straight through. Extending both refracted rays backward, they meet on the left side of the lens, beyond the object. The image is virtual, erect, and magnified. This is how a magnifying glass works. Here is a summary of all 6 cases for the convex lens, showing where the image forms and its type for each object position. Only case 6 gives a virtual image in a convex lens. In all other cases the image is real and inverted, forming on the right side of the lens opposite the object. The lens formula relates the object distance u, image distance v, and focal length f. The formula is 1 over v minus 1 over u equals 1 over f. Note the minus sign. This is different from the mirror formula which uses plus. Magnification for a lens, m equals height of image over height of object, which equals v over u. Note, no negative sign here, unlike the mirror formula. If m is positive, the image is virtual and erect, object is between O and F. If m is negative, the image is real and inverted, object is beyond F. The power of a lens P measures the degree to which it converges or diverges light. Power is the reciprocal of the focal length in meters, P equals 1 over F. The unit of power is the dioptra, symbol D. 1 dioptra equals 1 per meter. Convex lens, F is positive, so P is positive. Concave lens, F is negative, so P is negative. When 2 or more lenses are placed in contact, their combined power is simply the sum of individual powers, P equals P1 plus P2 plus P3 and so on. Practical use: optometrists prescribe lenses in dioptrace. A lens with power plus 2D has a focal length of 50 cm. A lens with power negative 1.5D has a focal length of approximately negative 66.7 cm, used to correct myopia.